Okay, hello everyone. I have received this question from a student. I would like to solve it. Okay, so what do we got here? We have a charge of uniform density, 0.8 nanocoulomb per meter, is distributed along the x-axis from the origin to the point x is equal to 10 centimeters. What is the electric potential relative to 0 at infinity at a point x is equal to 18 centimeter on the x-axis? So we have a few answers. So let me try to maybe do some sketch if I was able to do it. So let's say this is the rod. So it's a distribution of charge, right? So this is a rod. Maybe I could put a line so it could help me to. Okay, something like that maybe. So let's see. Okay, so this, let's treat it like one-dimensional rod. We have a distribution of charge and the point located somewhere here. So let's assume this is origin located somewhere. This is the origin, this is y-axis, this is x-axis, and this is the point. So x here is equal to 18 centimeter. This is x is equal to 0, x is equal to 10, and so on. Okay, so we have to be a little bit careful when we set the solution for this. So the first thing is we need to divide this into many small pieces, right? So let's show one of them somewhere here. Okay, now this piece carry amount of charge dq and it has a thickness, let's call dx. This charge is away from the origin by some distance, let's call it x. Okay, but when we set our equation for finding the potential at this point, okay, let's call point P. So every time I could refer to it as point P. So the potential at point P from that small piece dq, it's called dv. dv at point P is equal to k dq. Now I need to know the distance between dq and point P. Okay, so I need to know this distance. I need to know this dot distance. Okay, well, I know everything from here to here is 18 centimeters. So that dot distance is simply equal to 18, right? Or I could change it to, let's keep it at centimeter, or I could change it to, let's change it to meters. So it's 0.18 minus x, right? So let me erase this. So the answer here simply is equal to 0.18 minus x, okay? Okay, so we need to do integration. Why? Because we have too many other small pieces. That was only for the green highlighted piece, okay? Okay, so the left-hand side of the equation simply give us the potential at point P. That's what we want, right? And we know that x changed from 0 to 10 centimeters, so it's 0.1 meter, right? Well, one more thing, dq, by definition, dq is equal to lambda multiplied by dx, right? So I could substitute lambda dx instead of dq, which means that k is a constant. I could kick it out from the integral. Lambda is a constant, so I basically have the dx divided by 0.18 minus x and integral from 0 to 0.1. Okay, this is not difficult, right? The answer for this is equal to ln, right? Or actually minus ln. So this equal to lambda k ln, actually minus ln, of 0.18 minus x, okay? So we have the value from 0 to 0.1. And this should give us the correct answer of, looks like B is correct, is equal to V. Okay, so this is one way to solve problem, but to be honest, I get this from a student who got confused with this, right? And I know why the confusion was there. So there is another way to solve the problem. It could be easier for some of you. So I might actually do it here. There's another way to do that. So let me repeat, or let me do it in a different way. Okay. So here, it's the same rod, right? Let's see if I could copy paste this. Okay, so let's put it somewhere here. What I'm gonna do, I'm gonna simply just do one simple trick, right? Instead of putting the origin here, I'm gonna put the origin over here. Okay, so I'm gonna do this. I'm gonna just assume this is y-axis. I'm gonna assume actually the x-axis goes to the left. Usually, you know, I'm doing something against the notation because usually this is minus x, but I'm gonna say this is x. So my origin is here. Okay, which means I need to calculate the potential at origin due to the rod, which is the rod now is located to the left of me, to the left of the origin. Okay, remember we have 18 centimeters and we have 10 for the rod. So if this is 18, but I made 18 0, so this distance now it looks like 8, right? The distance looks like 8. So the beginning, because x, remember, is going to the left, so the beginning here would be 8 and the very end will be 18. Why 18? Because the rod is 10 centimeter. I'm here dealing with centimeter. Okay, so this is 8 and this is x is equal to 0. So I'm saying x is equal to 0, x is equal to 8 centimeter, x is equal to 18 centimeter, and I assume that the left side is the x-axis. So we're going to repeat the same thing again now. Let's divide the rod into many pieces. So this is the first piece, this is the last piece, and this is one piece I chose. Now you know that the integral, because first piece is located at 8 centimeter and the last one is 18. So it's no longer from 0 to 10 centimeter as the case of the, you know, of this solution. So what I'm going to do, I'm going to write my equation. dv equals to integration of k. Instead of dq, again, I'm going to write this. So it's equal to d lambda dx. But look out here. I need to know the distance between this piece and point O. The distance is just x because I named x, you know, to be the axis that goes to the left. So it's simply x here. Okay, it's simply x. It's not 18 centimeter minus x because in the first case my origin was to the left. Now my origin, I just changed the origin. Okay, but the limit of the integral is between 0.8 to 0.18 means 0.18, right? So if you do this integral, k lambda is going to be equal to ln x, and then it's from 0.8 to 0.18, and actually the same answer as before. So it's the same answer as before. I know, for me, I don't know about you, but for me actually this is easier, right, than to think about, you know, something minus something else. Okay, I hope this is this solution makes sense and it's clear. Okay, second question. So here we have the thin uniformly charged rod shown in this figure has a linear charge density lambda. Find an expression for the electric potential at point P. Again, this is distribution of charge, so we need to divide the rod into many small pieces, each carry a small amount of charge equal to dq, right? So the first piece located somewhere here, right? The last piece located somewhere, of course, at the end of the rod. Let's choose another piece which is somewhere in between. Okay, so now that small piece will carry a charge equal to dq, and it has a oops, what's going on? And it has a, let me erase this. So carry a charge dq, and it has a thickness dx. Okay, so we want to find the potential at point P, so I need to know the distance between point P and dq, which equals to r. But r obviously is equal to, this is b, now this equals to x, because this small piece is located away from the origin. Remember, this is origin, by x. So r is equal to x squared plus b squared under square root. Okay, so the potential through that from that small piece dq at point P simply is equal to dv equal to k dq divided by the distance, which is r, x squared plus b squared. Okay, so we need to do the integration to include all other pieces of the rod, knowing that dq is equal to lambda dx. So the left-hand side of the equation is simply going to give us v equal to constant. We could kick the constants out. Integral. So we have dx and x squared plus b squared. Now the integral, the first piece is located here. This is first piece. The last piece is located here. Last piece of the rod I'm talking about. Last piece. Which means the first piece is located when x is equal to a, so the integral starts from a. The last piece is located at the position when x is equal to a plus l, so it's equal to a plus l. Okay, now I'm sure you have done this in calculus. Whenever you have this integral dx x squared plus b squared, okay, if b, of course, constant, if this is constant, this integral simply is gonna give us at ln the variable, you write the variable here, plus the expression in the denominator, so it's equal to x squared plus b squared. Okay, so which means the answer simply is equal to k lambda ln of the variable, which is x in this case, plus the expression, which is this expression, you write it again here, x squared plus b squared. And then the limit of the integral is from a to a plus l. So what do you do? Instead of x, once you put a plus l, and then once you put a. So let me erase this one here. Do the next step over here. So that simply is going to be equal to k lambda ln, instead of x, I'm going to write down a plus l plus, again, a plus l squared plus b squared. So it's going to be equal to a plus l squared plus b squared. So this is done minus ln. I'll repeat this again, so is equal to x now is going to be a plus a squared plus b squared. Okay, and now you could do one more thing. You know that ln, let's say a minus ln b, you can write it as ln a divided by b, right? A and b, so let's say this is our a and this is b. So you can write in a little bit maybe compact way. The answer could be equal to k lambda ln, let's say this term, I don't want to write again, this term you write it here, and this term you write it here. Okay, so that's the expression. Okay, hope this is clear. Okay, this is the third question. We have a rod of length L lies along the x-axis with its left end at the origin. It has a non-uniform charge density of lambda equal to alpha x, where alpha is a positive constant. So we have A, B, two requirements. First, before I go through the requirements, very important that the origin is located here. I mean, the question, specify this is y, this is x, so our origin is over here. Okay, so the first question is, what's the unit of alpha? Well, should be easy because lambda is a linear charge density, right? So if this is linear charge density, you could just maybe check it with unit. So it's charge coulomb divided by meter, okay, as a unit. And alpha, let's say we don't know the unit of it, and x is a meter, right? So the unit of alpha should be equal to, so alpha in this case as a unit equal to column divided by meter square. Okay, second question, which is, let's say, more important. Finding the electric potential at point A. So this is like a typical question, distribution of charge. We need to distribute the rod into many small pieces. So the first piece, let's say, located here, the last piece located here, and let's show one of the pieces somewhere here. So this one carry a small charge dq, it has a thickness dx, it's away from the origin by a distance x. Okay, but remember, we need to find the potential at point A. So the potential at point A from that dq is equal to k dq. Now the distance between the point dq and A is actually x, or let's say d plus x. Okay, d plus x, because the origin is given here. If the origin was given at point A, you could have just called it x. The distance r, you could just call it x, but now it's d plus x. So we need to do integration. Remember, dq is equal to lambda dx, but our lambda is not constant, so the left-hand side will be simply equal to the potential at point A equal to, instead of dq, I'm going to say lambda, but lambda is alpha x. So I'm going to take k outside, alpha outside, and then the integral will be basically x dx divided by d plus x. So let's figure out from where to where the limit of integration. Well, the first point on the road is located at x is equal to 0, so x is equal to 0. And the last point, so this is actually x equal to 0. The last point is x equal to L. Okay. This integral, I'm sure you have done it in calculus, but maybe one way to do it is, let's change the variable. Let's say d plus x is equal to u. Let's just call the new variable u. Means, let's do the derivation of the both sides of this. So it's 0 plus du is equal to dx equal to du. Let's find x. Also, x here simply is equal to u minus d. Okay. I'm going to keep the limit of integration as x, because you could also change the x is equal to 0 to see if x is equal to 0, u is equal to d, right, according to this. But I'm going to keep the limit of integration as x. In a second, I'm going to explain why I do that. So this is basically is equal to k lambda integral. I want to write x0. X is equal to L. I am still keeping x as x here. I'm not going to change it to L, because then I'm going to bring u. I'm going to bring the variable u, change it back to x. Okay. So let's see how this look like. So our x is equal to u minus d. So it's u minus d, right? Multiply. Our dx is du, and our d plus x is u, right? So this is basically equal to, this is equal to k lambda equal to integral of u divided by u is 1, so integral of du minus d will be constant, integral of du divided by u. Remember, I am still keeping the limit of integration as x. Okay, so this equal to k lambda, this is u, minus d ln u. Because I kept the limit of integration with x, I'm going to put back the ku. I'm going to change back u into the original variable. Remember, u was d plus x, so it's d plus x, right? Minus d is d, ln u means ln d plus u. Okay. Now you say from x is equal to 0 to x is equal to L. Okay. So this is going to be easy. Instead of x, instead of think this is X, right? The last one should be X. This is a typo. Should be X. Okay. So instead of X and X, once you substitute L and once you substitute 0, and the final answer, would be an expression, okay, given. Okay. So I hope this is clear. Now you could have changed, as I said, the limit of integration from X to U, and then finish everything, and at the very end you bring back, or you change back U into X. But here, no, before I substitute this value into the expression, I change U. I brought U back to its original definition. Okay, so this is okay. Let's consider this question. We have 4 identical particles, each having charge Q and mass M, are released from rest at the vertices of a square of side L. So the question says, how fast is each particle moving when their distance from the center of the square is double? Okay, so let's explain this. So initially you have 4 particles. They have the same Q. One here, one here, one here. Usually if I have multiple point charge, I call it Q1, Q2, Q3, but because they have the same Q, so it's not important to call them 1, 2, 3, 4. Okay, so the distance between the sides are L. The distance from the center, it's actually, we need it, so let's calculate this distance. Let's calculate this distance. Okay, now this distance, it's obvious. This equal to L divided by 2. You square it plus L divided by 2. What's going on? So it's equal to L divided by 2 square plus L divided by 2 square. So this equals to, so it's a fourth L square, so it's L divided by root 2. L divided by root 2. Okay, so let's call it S. This one, S is equal to L divided by root 2. Okay. The question says, how fast is each particle moving when their distance from the center of the square doubles? So that is when these particles are released, the square gonna get bigger. So that is get doubled. So this is new S prime, let's say. So now S prime is gonna be 2L divided by R square. Okay, when this happens, actually L also going to change from L to L prime is going to be equal to 2L. Okay, so the moment we knew that, it's not very difficult actually to go through the solution, but there's something else within the solution I'm going to explain. So in this case, you have particles, start from res and then they get faster. So maybe think about the conservation of energy. We say delta K plus delta U is equal to 0. Okay, so kinetic energy is equal to, I call it final minus kinetic energy initial plus U final minus U initial equal to 0. Final means here, so this is F, and initial means here. Okay, well, final kinetic energy is equal to half mv final square. But now I have 4 of those, so the m has to be multiplied by 4. So this term need to be multiplied by 4. Okay, it looks like every term need to be multiplied by 4. Okay, so maybe at the end I'm going to just multiply things by 4 plus u final. So what's the initial minus u initial equal to 0? So I need to explain what are these terms. These are the electric potential energy, right? So first we need to understand, if you have 2 charges, Q1, Q2, what's the potential energy for, what's the work needed to maintain these 2 charges next to each other by a distance r? Well, the potential energy is basically equal to K, Q1, Q2 divided by R, right? But now you have 4 charges. So when you have 4 charges, you don't have one term. Actually, you have 6 terms. Let me explain. So you have 6 terms like this. Okay? Let me explain this. So you have Q, 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 Q. Let's make it general. 1, 2, 3, 4. So there is one term between these two. There is Q1 with Q2. There is another term Q1, Q3. There is another term between Q1 and Q4. So that's 3 terms. Okay. Now, Q2 also will have a term with Q1. It's already there. There's a term with Q4. So this is another term. And Q2, there's a term with Q3. Okay, so now how many terms we have? 1, 2, 3, 4, 5. There is one more needed. Q3 also with Q1, Q2, Q4. So there is another term. So we have 6 terms. We need to write this 6 terms. But in our question, because Q's are the same, 4 terms. Let me highlight it so you know what I mean. This term, this term, this term, this term are the same, and the 2 diagonals are the same. So the U final and U initial can be written in the following way. Okay, so I'm going to write it U final equal to. Remember, I have 4 terms. I have 4 terms of those. So it's 4 multiplied by adjacent, mean these two, equal to K. Q times Q is Q squared divided by L. Okay. Plus, I have 2 diagonal terms, so I'm going to say 2. Still, actually I did one mistake. Because I deal with the final, so I'm dealing with the large. I'm dealing with the large rectangle. So the distance, this distance is not L, actually is 2L, right? 2L. Okay, the 2 diagonal one is equal to 2 K, Q times Q, Q squared. This diagonal term turns out to be 2L divided by root 2. So it's equal to 2L divided by root 2. Okay? This term, from very beginning, we need to multiply by 4. Let's not forget this. Okay. U initial equal to, you repeat the same thing. We have 4 terms, adjacent terms, so is equal to K, Q squared. Now we are dealing with the small rectangle, so it's actually the distance between adjacent terms is L, plus we have 2 diagonal terms, K, Q squared. The diagonal term, so it means S plus S, S plus S. So this has to be multiplied by this one, was actually half distance, right? Half, but we need double of this, so we need to change this into 4. Okay, so it's a Q squared here. For the small rectangle, S is equal to L divided by 2, but we need S plus S because this is the whole distance, right? So it's 2L divided by root 2. Now we need to combine everything here. So I'm not going to do this, so you put everything back here, and you solve it for V final. So V final in this case will be a long expression. Okay, so that's how you do it. But the most important thing, be able how to find the potential energy of 4 charges next to each other. Okay, so I might maybe repeat this because this is important. So that was the solution for this. And I just would like to repeat the calculation of the potential energy for 4 charges, just to make things clear. Okay, so let's think about it again. We have Q1 here, Q2 here, Q3, Q4. Okay. If we want to find the potential energy of this combination of charge, potential energy is equal to. For two charges, this is the term that we write, K, Q1, Q2 divided by R. But here Q1, interact with Q2, so there is one term. Q1 interact with Q3, this is the second term. Q1 interact with Q4, so there is another term. Okay. Now repeat it for Q2. Q2 is interacting with Q1, is already included. Q2 with Q3, so there is this term. And Q2 with Q4, so there is this term. 1, 2, 3, 4, 5. Now let's move on to Q3. Q3 interact with 1, 2, 4. 1, 2 already there, so now we have 6 terms. But remember, this term, this term, this term, this term, the same, because Q1, Q2, Q3, Q4 are the same. But these two terms also the same with each other, right? So now the total U for that combination is equal to, you have 4 terms of K. Q1, Q2 means Q squared, divided by the distance L, plus you have 2 diagonal terms, so it's K, Q squared. You have the distance, so you have, this diagonal distance, right? So we know that half of it is L divided by root 2, so we need the whole of it, so it's equal to 2L divided by root 2, okay? By the way, you could write this one as, root 2L root 2 divided by root 2, right? So this with this, you could simply write it like this. Make it nice, okay? This is it.